Matthews Gatos here. In this video, we are going to look at the intermediate value theorem. So let's get started. Before I can talk about the intermediate value theorem, I need to talk about continuous functions. So a function is considered continuous on some closed interval a and b, those are x values, if it takes on every value between f of a and f of b. So remember function notation, you're taking your x value a and you're plugging it in here. That's your y value that corresponds to a. For b, you're doing f of b. That's a y value that corresponds to x equaling b. So it's continuous if on that closed interval, it takes on every single value, which means it can't jump over or skip any value between f of a and f of b. So that's what a continuous function is. If we're ever in a situation where we need to prove continuity, remember this continuity statement that we learned in class. The limit as x approaches a of f of x, if that is equal to f of a, then f of x is continuous at x equal to a. So now that we know, refresh our memories on what continuous functions are, let's look at the intermediate value theorem. So if f is a continuous function, again on a closed interval a and b, those are your x values, and k is a number between f of a and f of b, it means that k is a y value. Now those endpoints can't be equal. If those conditions are met, then the intermediate value theorem guarantees at least one value of c, and that's an x value, in the open interval a and b such that f of c equals k. Well, what does that mean? Let's break this down into the conditions. Okay, so three conditions have to be true. So condition number one, f of x is continuous on a closed interval. That is an essential step and you have to state it and why it's continuous. Condition number two, the endpoints f of a and f of b are different values. They can't be equal. And the third condition, k, that's a y value, has to lie between f of a and f of b. So k is the y value when x is equal to c, so f of c. Those are the three conditions that have to be met. If those three conditions are met, we need an end statement. It's really important that we do this in the correct terminology. So after you show the three conditions are true, I want you guys to commit this to memory. By the intermediate value theorem, there exists at least one value c, and that's an x value, in the open interval AB such that f of c is equal to k. Now, obviously, when you're stating this, you're going to replace a, b, and k with the actual values, but this is the end statement that I want you to commit to memory and apply. Let's look at this graphically, what we're talking about. So say I have some x value a and the corresponding y value f of a, and then I have another x value b and the corresponding y value f of b. So if I were to connect these left to right, reading the graph left to right, I would have an increasing function. So let's pretend that's my function. So let's go through the requirements. Number one, f of x is continuous. Yes, there are no breaks in the graph. Condition number two, my endpoints are not equal. That is true. Okay. Condition number three, there's some y value k that lies between f of a and f of b. Okay, so we've got some y value that lies between there. The intermediate value theorem says, therefore, there is some value c that lies between a and b such that f of c is equal to k. That's what it looks like graphically. Now let's look at a decreasing function. So I've got some value a for x and the corresponding y value f of a. I've got an x value b and the corresponding y value f of b. So you can see reading this graph from left to right, if I were to connect the dots, it would be a decreasing function. Let's go through my three requirements. Okay, number one, it's continuous. Yes, there's no breaks. Number two, the endpoints are not equal. Also true. Condition number three, there's some y value k that lies between these two values. Okay, all three conditions are met. So the intermediate value theorem says there is at least one value of c, and that's an x value, such that f of c is equal to k. In other words, the c value, if I plug it into the function, I'm going to get that y value for k. So the intermediate value theorem, is an existence theorem. So what that means is it guarantees there's a value, and that's an x value, existing. It doesn't tell us what that c value is. It just guarantees that there is at least one. Okay, so let's go through some examples. So here, I want to show that f of x has at least one real root on the interval 1, 5. So first thing we have to do, go through our three little steps here. So is f of x continuous on this interval? And it's a polynomial. Polynomials are therefore continuous everywhere. So condition number 1 is met. Okay, condition number 2, find my endpoints. Find f of 1 and f of 2. So f of 1 means I replace x with 1 and I do the number crunching to figure out what the y value is. Okay, so 1 cubed, take away 1, take away 2, that is -2. Now let's do f of 2. So replace your x values with 2. Okay, so I can figure that out. So 2 cubed, take away 2, take away another 2 is 4. Okay, so I can see that my endpoints are in fact different values, -2 and 4 different values. Okay, third requirement, show that k is in between f of 1 and f of 2. So since I want at least one real root, that's an x-intercept, my y value is 0. That's my k value. So I want to show that k for 0 is in between f of 1 and f of 2. So is it between these two values? Well, let's check. 0 is in between -2 and 4. Yes, that is true. So 0 is in between -2 and 4. That condition has been met as well. So all three conditions have been met. So let's try our end statement. Can say by the intermediate value theorem, there exists at least one value c in the open interval 1 and 2, such that f of c is equal to 0. That would be my end statement. Okay, let's try another example. So I have f of x. I want to know, can the intermediate value theorem in the interval 0 and 2, can we guarantee a value in between 0 and 2 where f of x is equal to 1? Okay, so let's go through our three requirements. Number 1, is f of x continuous? So f of x is a polynomial. Polynomials are continuous everywhere, so I'm good there. Okay, let's figure out what f of a and f of b are. So these are my a and my b values. So f of a, that would be f of 0. So replace x with 0. Like that. And number crunch that out, and I get -2. Let's do the same thing for b. So f of 2, plug that in. So I've got 2 times 2 cubed minus 10 times 2 minus 2. So f of 2 is equal to, number crunch that out, I get -6. So requirement number 1 is met, requirement number 2 is met. The endpoints are not the same. Let's look at requirement number 3. Is k in between there? So this is my k value here. So I want to know, is 1 in between f of a and f of b? So f of b is smaller, f of a is bigger. So I want to know, is this true? So f of b was -6. Does that mean that 1 is in between -6 and -2? So you can see that this requirement is not met. So since all three have to be met and that one doesn't meet, this I cannot use the intermediate value theorem. So here's my end statement. The intermediate value theorem does not apply. Therefore, we cannot guarantee a value c in between 0 and 2 such that f of c equals 1. Okay, so there might be one. We don't know exactly what's happening in this function unless we were to graph it, but we can't use the intermediate value theorem to guarantee it. Okay, let's try another one with a table here. So f of x is continuous with values given in the table. What's the minimum number of zeros of f of x on the interval 1 to 11? Okay, so let's go through our three requirements. So is it continuous? Yes, given in the question, it's continuous. Okay, number 2. I want to know, do my endpoints equal? So look at all the different intervals in between here. So basically what I need to look at is all of the y values. And I can see for all of my y values, none of them are equal. Okay, so f of 1 doesn't equal f of 3, 5, 7, 9, or f of 11. Okay, so statement number 1 and number 2 are met. So now we're going to look at k being a number in between those. So we're looking for zeros. Zeros are roots, x-intercepts. All of them have a y value of 0. So let's go through this table here and look at each one of the intervals and see if 0 lies in between there. So in my first interval, between 1 and 3. If you look at between 1 and 3, my y value is 4 and 2. So there's no chance of it going and crossing the x-axis. So that one doesn't work. Let's look at my next interval between 3 and 5. So between 3 and 5, look what happens. My y value changes from positive to negative. So I know that 0 lies in between these two values. Okay, let's look at my next interval between 5 and 7. So between 5 and 7, I'm at -1 and I'm still at negative. So I'm going more negative. So that interval doesn't apply. Let's look at the next one between 7 and 9. So between 7 and 9, I'm at -3 and I come up to 1. So I must cross the x-axis somewhere in between there because 0 is in between -3 and 1. And then my last interval between 9 and 11. You see I'm at +1 and then I go down to -5. So somewhere in there I have to cross that x-axis because 0 is in between -5 and 1. So because of those, we can see that there are 1, 2, 3 different values. So here's my final statement. By the intermediate value theorem, there exists at least 3 values of C in that interval 1 and 11, such that f of C is equal to 0. Okay, let's try another one. In this one here, given the function f of x is equal to 1 over x minus 2, can the intermediate value theorem guarantee a value in the interval 1 and 3 where f of x is equal to 1/2? Okay, so let's go through our 3 requirements. Okay, so requirement number 1, is f of x continuous? So this is a rational function. We cannot divide by 0 here. So I know that it's not continuous at 2. So check, does that lie in my interval? So my interval is 1 and 3. Now 2 is in between 1 and 3. So that means that it is not continuous. So since this first one fails, it doesn't even matter what the other two say. So I can cross off if it's not true for condition number 1, it's not true for condition 2 and 3. Okay, so the intermediate value theorem fails here. So the intermediate value theorem does not apply. We cannot guarantee a value C in the interval 1 and 3 such that f of C is equal to 1/2. Okay, one last question here, and this is a typical type of question that you might see on the AB exam. So, several values of a function f of x are given in the table below. Which of the following conditions is enough to guarantee there is a value C in the interval -4 to 4 such that f of C is equal to -5? Okay, so let's go through our requirements. Okay, so requirement number 1 is f of x continuous. So it doesn't say anywhere in that question that f of x is continuous. So for me to know if it crosses -5, like I can look between here and here, it doesn't cross. Between here and here, it has to be -5, somewhere in between there and there. Between here and here, it doesn't apply, and between here and here, it doesn't apply. The only way that I can guarantee that there is a value C where f of C is equal to -5 is this very first condition, that it is continuous. So I know for sure that is one of the options. Now let's look. Does it matter that f is increasing? So remember when I first introduced this to you, I showed you whether it was increasing or decreasing. The intermediate value theorem applies in both, so this doesn't matter. And then the next one, f is defined for every value in between -4 and 5. Does it matter that it's defined in every value? Well, if it's continuous, it's automatically defined for every value. So statement number 1 accounts for statement number 3. If it's continuous, it has to be defined. So which of the following is enough to guarantee it? This is true. We need this to happen, but continuous, because it's continuous, means it exists. So really all we need to have is option A, number 1. That's all we need to guarantee. Okay, so last thing that I want to use the intermediate value theorem for is to answer this age-old question. Why did the chicken cross the road? Of course, the answer to that, because of the intermediate value theorem. So I hope that this video helped, and I look forward to seeing you for the next one. I need